Word. Okay. I wanted to go over to, let's see, over here, and I was going to pull up, where are they? The labs. Okay, 2 seconds. I had it pulled up somewhere, but obviously not right there. Go to chemistry, general, nope. Okay, let's try this again. All right. You should be able to see experiment number 5. Nope, that says 7. Number 5, come on. Okay, can you guys see experiment number 5 up there?
Yes, we can hear it.
Okay.
And we see it.
Excellent. Okay, so this is the one that most of us got finished with last week. I just wanted to highlight it because that's going to take us into what I'm going to help you with today. So you went through a whole bunch. Come on, da, da, da. You went through a whole bunch of chemicals and you came up with the pH using the indicators, the pH paper, and some of you didn't quite get to the pH meter, but all of these. Oh, hold on, I have to cough again. Does that really mute, or am I coughing in your ears?
It mutes.
Ah, excellent. Okay, so we're going to look at mostly these top ones, not necessarily the household chemicals. And then we're going to see what we should have gotten. Okay, so we're going to do 0.1 molar HCl, the 0.1 molar phosphoric, and so forth. So let me go back up here. Whoops, I wanted to do the pre-lab. Come on. All right, so just generically, what is a Bronsted-Lowry? Proton donor, proton acceptor. Okay, so proton donor is the acid, base is the acceptor, pH is the negative log of the proton concentration. Acidic means a pH anything less, whoops, that says pH, anything less than 7. All right, this is the one that I wanted to practice on though. What is the proton concentration of a solution that has a pH of 2.0? So 2.10 is equal to the negative log of the proton. And so multiply both sides by negative.
Once you print it out with you guys, she only gave me 2 pages.
All right. And so 10 to the negative 2.1. 7 let me see, sig figs, 7.9 times 10 to the minus third. All right. I'm not surprising anybody, right?
Nope.
Okay. All right. Then we went through and did all of these, and the post-lab questions was, ooh, okay, what was your most acidic solution? And almost everybody came up with a pH of 1. All right. So I noticed a couple groups came up with that from the pH meter, and a couple just said the pH paper worked better. But the HCl solution was a pH of 1 on there. Okay. One of the readings off of the meter was 1 point, I think 10. So we're going to work with that number. That was the most acidic reading that we got. And so I just wanted you to be able to get back and forth between it. So 1.10 is equal to the negative log. And so multiply by negative, take it to the 10. So the concentration in that solution based on this pH reading was 7.9 times 10 to the minus 2. All right. The important part in lab is that the concentration that we expected? So that bottle was labeled 0.10. Okay, that bottle was labeled 0.10. Based on the pH meter reading, it was only 0.0794. So who do we trust? Who do we trust? Okay, now I'm going to trust this one because, well, I'm the one that made it. Oh, yes, Aisha.
They're wondering if these are the answers for this question.
Yes, these are the answers. So almost everybody should have come up with a pH of 1 as their strongest pH. Okay. And it should have been the 0.1 molar HCl. So of all the ones that we tested, that should have been the most acidic. And then hopefully when we meet on Thursday, we're going to play with those meters until we can get an exact pH of 1 so that we can trust that the meter and the concentration are telling us the same thing. This one is going to vary. Okay, so a lot of you will come up with a pH of 9, pH of 10. So this one, whichever one that you have the least acidic, it doesn't matter on this one. You would do the same thing and come up with a concentration, but know that everything I gave you was 0.10 molar. So when you do the anti-log, it should be close to the 0.1 molar. Okay, that was the whole point of this lab, is number one, to just get familiar with the indicators. 2, get pHs from the paper. And then the one that we're going to have to start to trust is the pH from the meter. Okay, because this is the one that we're going to be using for all of the next labs. So on Thursday, everybody is going to pull out their own meter. And so each station has one. So everybody would have their own meter. And then we're going to play with it, or it's called standardizing it, until we have exactly the pHs that we're supposed to get. Okay, well, that begs the question, well, what if I made the solution wrong in the stockroom for you? We're actually going to test that. Okay, so that's the beauty. That's how we're going to start Thursday. But some of you got these numbers already. Okay, so on experiment 6, once we were familiar with the meter and the paper, we were going to take, come on, okay. We were going to do these solutions, and literally the whole lab, oh, stop. The whole lab was taking the pH of 9 solutions. Okay, it takes 30 minutes or less. All right, this is what we were going to find. Okay, so for 0.1 molar, before I start, did anybody get this far? Does anybody have data that I can use from lab?
No.
Okay, so these are the numbers that we're going to play with then. So these are going to be the predicted numbers. We're going to predict them today. You are going to do this in lab. It'll take the 30 minutes and make sure that your pH meter is giving you the numbers that we expected. Okay, so before we go on, let's just identify what in the world we're doing. This is 0.1 molar acetic acid, so that's just a weak acid. 2 milliliters of acetic acid and 2 milliliters of water. Well, it's still just a weak acid. but I diluted it. So 2 mils plus 2 mils. So I doubled the volume. So now I half the molarity. All right. 1 milliliter of vinegar and 49 mils of water. Again, that is just a dilution. So that one's a dilution. That one's a dilution. And M1V1, M2V2. Let's see. So 0.1 times 1 milliliter is equal to M2 times 50 milliliters. So the concentration there is 0.002. All right, number 4, 2 milliliters of vinegar plus 2 milliliters of acid. Okay. All right, step number 1. Who is your weak? It's the vinegar. Did you add something to it? Yes. Was it just water? No. Is it already part of the equation? Yes. This one's a common ion. All right. Is it the special common ion called a buffer? No, it is not a buffer. And it is getting diluted. Okay. Phosphoric acid is just a weak acid. Ammonia is just a weak base. Nothing's added to those. 5 milliliters of ammonia and 20 milliliters of water. That is still a weak base, but it has been diluted. And so we need the concentration. So 0.1 times 5, 25. So that new dilution is 0.02 molar. 0.1 molar ammonium nitrate. Okay, remember, don't care about the nitrate. This is just ammonium, so this is a weak acid. And 2 milliliters of ammonia and 2 milliliters of ammonium. That is the special combination called a buffer. All right, so before I get down to the numbers, at least I know what to expect. All right, let's see these pre-lab questions. Define the term acid ionization. Well, that's how many protons come off. The common ion effect is when Le Chatelier shifts when it's already part of the equation. We're actually going to be doing this in just like 2 seconds. So we'll do it on the other page. And then we just did this. Okay, we just did this piece. So solutions 1 through 9, who would exhibit the common ion effect? Okay, let's go back up here. Who has a common ion? Well, this one does. And this one does. Anybody else? Nope. So solutions 4 and 9. So 4 and 9. Okay, one of them is just a common ion, and one of them is the special one called a buffer. All right, which of them are simple dilutions? Who did we say? So that's number 2. It's number 3. Okay, now number 4 is not just a simple dilution because that's not just water. And number 7. So 2, 3, and 7 are just dilutions. And then what strong acids did I have? There was some HCl. Weak acid was vinegar and ammonium. Weak bases was ammonia. And I think I had some sodium hydroxide in there. So I'm just going through and now identifying them as weak acids and strong acids. All right. So vinegar was weak. Oh, phosphoric was weak. Yes, Aisha.
I think they wanted to see, was it the next page?
They wanted to write it down.
They wanted to write it down, the answers.
Oh, okay. And let me look and make sure. Okay. All right, so the only strong acid I saw over there was HCl. This one had 3 in its column. Weak bases was only NH3, and I think there was 1 mention of sodium hydroxide. So as weird as it is, those are the only chemicals that we're playing with in this particular lab. Okay, give me a heads up when everybody's done writing.
We're good.
Okay. Okay. This is the whole lab, by the way, is right here. You would now go and make all those solutions, put the pH probe in it, and have those numbers. So we are going to predict what you should have seen. And I actually put a place for you. All right, post-lab question number 1. You had 0.1 molar vinegar. Now we've done this problem like 6 billion times, but it's HAC. We started with 0.1 molar. All right, so we have done this one before, and X is 1.3 times 10 to the minus third, I believe. Yep. And then yes, it's good. Yes, we can ignore water. All right, so we come up with a pH of 2.87. I'm just going to put a little note to myself right here. X is equal to 1.3 times 10 to the minus third. Okay. All right. Holler when you're ready for me to go on.
Everyone good?
Okay.
Oh, give us just a second.
Okay.
We're good.
All right. The next one, okay, was just a dilution. So we're going to have the exact same problem, but with a different concentration. Now, I did this for a reason. This concentration turned out to be 0.050 molar. So going to do the exact same thing, going to ignore the X, going to check it. So X is 9.5 times 10 to the minus fourth. Going to check that. So 0.05 times 100. 1.9%. So we're still good. And take the negative log of that. Is 3.02. Okay. Does that make sense? Well, yes, I diluted it. It was a weak acid and I diluted it so it's not as concentrated, so it shouldn't be as acidic. All right, give me a heads up when everybody has that written down.
We're done.
Okay, all right, here's the tie together that I was hoping everybody would see. Solution 3 was diluted even more. And let me see, I'm gonna have to jump up there and see. I think it was 0.002 molar.
Yes. Yes.
Okay. So gonna do the same thing here. Gonna ignore the X. And so 1.9 times 10 to the minus fourth. And that doesn't look right. 1.8. Yep, it is right. Okay, so 1.9 times 10 to the minus fourth. All right, divided by that. Oh, it's not the X. Times 100. Oh, 9.4%. 9.4%. Okay, so that was supposed to be the big jump here. I am so dilute. I'm so dilute that ignoring this X now is a no-no. Okay, it's a no-no. All right, we can either go back and we can do the quadratic, or we could do successive approximations. So whichever you want to do, but I'm going to do that successive, which means I take the answer that I get and I subtract it from my initial concentration. All right, so 0.00181, and then I'm going to check it. Okay, so I'm sorry, I'm not going to check that. That's what I'm going to use as my concentration. So 1.8 times 10 to the minus fifth is equal to x squared over 0.00181. Is 4.2 times 10 to the minus third. Okay. Gonna see if my little assumption was valid again. Divide it by the 0.00181. And that was a flop. Hold on. 1.8 to the negative fifth. 0.00181. Square root is 1. That's why. Sorry, this is not. It's not 4.2. That should be 1.8 times 10 to the minus fourth. Going to divide that by 0.00181.
AC is confirming with the quadratic formula.
Oh, excellent. Ah, because this is still 9.9%. In the end, if we do it 3 times in a row, the answer will come out to be 1.8 times 10 to the minus fourth. But Izzy, as soon as you're done with that. So after 3 successives, the X comes out to be 1.8 times 10 to the minus fourth.
Okay, it looks good.
Okay. And I don't care how you do it. You can jump straight to the quadratic. You could do those successives, whatever works in your world. Okay. Now take the negative log of that. And that pH is 3.74. All right. So I'm going to go put that up here. 3.74 x is 1.8 times 10 to the minus fourth. And the second one was 3.02. And its value was 9.5 times 10 to the minus fourth. All right, before we go any further, are there any questions on how I found the X and the pH for those solutions?
No, any questions?
Okay. The beauty of this is it's supposed to sing to us now. I'm not sure it's going to be singing to you right now, but if you will notice, this is 0.1213. This one is 0.12395 and 0.12318. Those X's are getting smaller. What is X? X is how much it's ionizing. X is how many protons are coming off. And we just showed that guess what? As you get more dilute, you get to be a weaker acid. And so therefore you ionize less. Okay, now I'm doing little cartwheels right here, but you're not. But I wanted numbers, I wanted math to tell you exactly what we knew. Every time you dilute, that is a weaker acid, which means it will even give up less protons. Okay, and that is our number crunching values for it. All right, well, thanks, Jolly. I'm not sure that was very interesting, but okay. So for those three, that was the whole purpose. That was the whole purpose. On solution number 4, let me see, solution number 4, I'm going to have to peek back up here. Solution number 4, come on, come on, come on. Solution number 4 is 2 mils of 0.1 and 2 mils of 0.1. I'm going to jump over to my whiteboard because it's easier to get around in. All right, so I have 2 milliliters of 0.1 molar acetic acid and 2 milliliters of 0.1 molar HCl. Okay, step number 1, I have to have an equation. And so I'm going to go with my weak. Okay. All right. Did I add anything to it? Yes. Don't care about the chlorine. I added protons to it. Okay, now 2 mils and 2 mils. I have diluted both of them to 0.05 molar. All right, so 0.050, 0.050, and 0. Here's the key though. This is a common ion, so it's not starting at 0 because I've added it. But I'm still going to plug it into my Henderson-Hasselbalch. Not Henderson-Hasselbalch. I'm going to plug it into my equilibrium expression. All right, so 1.8 times 10 to the minus 5th is equal to 0.050 plus x times x divided by 0.050 minus x. All right, you can ignore the plus and the minus x. Oh, look, they're the same. They're the same. So the x is 1.8 times 10 to the minus fifth. All right, here is the first time where x is not what we take the negative log of. Okay, what is x? X is just the ionization, but I started with some protons already. So if you want the proton concentration at equilibrium, it's 0.050 plus 0.123418. And there is the reason for this problem. It's negligible. Wow, you'd think I could be done coughing by now. I just got up and took cough syrup though. So that's a nice thing about being at home. Okay, so the key here is we found X. The whole point of these first three problems is to really give you a feel for what X is. X is how much ionized from the weak acid. Okay, that's not always going to control the pH because in this case, who cares? This came from the strong acid. This came from the weak acid. Well, that is so tiny, it's just negligible. So the one that's controlling the pH is actually the strongy. So every time I've said that in class, I wanted it to be very obvious. Oh, based on real numbers, the strongy is actually controlling the pH. So the pH is actually the negative log of 0.050. And so we should be expecting a pH of 1.3. I'm going to go back to our lab table and I'm going to plug that in. All right, so 1.3. Whoa. Okay. We should have expected that. Now, the fun thing in lab, if you do the experimental portion first, in lab, everybody thinks that they've done something wrong. Because here we have a pH of 2, pHs of 3, and then suddenly it plummets. But now looking at the numbers, we should have expected it to plummet because basically we're taking the pH of a diluted strong acid. All right, any thoughts, questions on what that one was supposed to show us?
Nope.
Okay. All right, let's go to the next one. So 5 is is phosphoric acid. Okay, now this one's painful. The reason that I did this one, well, is because it's painful, but I wanted you to see phosphoric acid has a pretty low pH, but technically it's not one of our strongies. And so the whole purpose was, hey, what is phosphoric acid? Okay, we're only going to deal with one of the protons coming off. So we're only going to be dealing with the Ka1. And we started with 0.100. And I'm looking at my chart, and the Ka1 of phosphoric is 6.9 times 10 to the minus 3. Okay. And I am hoping at this point, you're setting these weak acid and weak base equilibrium problems. You're setting them up really quickly, and you're able to, chunk right through them really quickly so that, the buffers and the titrations are actually where we're concentrating on now, not just the weak acid base. So 6.9 times 10 to the minus 3 is equal to x squared over that. We're going to ignore x. X comes out to be 2.6 times 10 to the minus 2. Got to check. All right. There's the reason for this problem. Okay. When we do those checks, it's not just because I said so. It is actually supposed to be telling us something very important. 26%. Okay. It's saying I'm not weak. 26% of those protons are going to come off. So therefore, you can't ignore X because there is a whole bunch of them coming off. So in this case, you have to do either the successive or the quadratic. But while this is a weak acid, so it's not one of the 6 strongies, it's still fairly powerful. Somebody wants to do the quadratic while I do the successive, feel free. All right, so I'm going to take 0.100 minus 0.026. Okay, so now I have 0.074. So it is 6.9 times 10 to the minus 3 is equal to x squared over 0.074. And that is 2.3 times 10 to the minus 2. So it's not a big difference. It used to be 2.6, now it's 2.3. But I'm going to divide that by 0.074, 100, and I'm at 30%. Okay, so if you divide it by this one, it's 30. Whoa, that's a 3. 30%. And if you divide it by the original, okay, the original 0.1, and I don't care which way you do it, as long as you're consistent. Oh, now I'm at 23%. Okay, so just as I came up with before. Terrible, terrible, terrible. 23%. I still can't use it. So we're going to go one more time. And we're going to subtract the 0.023. And see, you're probably already done with the quadratic by the time I get done with this one. Now I'm going to plug that in. 6.9 times 10 to the minus 3 is equal to x squared over 0.077. So x is equal to 2.3 times 10 to the minus 2. All right. You know you're
Yeah,
done.
we got it too.
Is that what you came up with?
Yes. Yes.
Okay, maybe I should have just gone quadratic because that was obviously faster. The way you know that you are done doing successive approximations is you will either get two that are the same, or this one might be slightly higher. Okay, so that's how you know you're done. And it's telling me that it's 2.3 times 10 to the minus 2. Now, after all that math, I've forgotten, well, what was I supposed to be doing in the first place? Well, x, plug it into my ice table, is 2.3 times 10 to the minus 2 molarity. And so my pH is 1.64. So the reason I put phosphoric acid on here is it is not one of the 6 strong acids, but that doesn't mean it doesn't, ionize, but it has like a 26% ionization at 0.1 molar. So it still puts out some significant protons. Right? All right. So I wanted you to see phosphoric. I wanted you to see that it was fairly acidic, and either the quadratic or the successive approximations. Okay, so that was the purpose of this one. And so 1.64. 1.64. And the next one is ammonia. All right, I should make a little note to myself right here. So this is HAC, HAC. This one was HAC plus protons. This one was phosphoric. And this one's going to be ammonia. All right, I'm going to go over to the whiteboard. Okay, now ammonia is a base, so this time I'm expecting a basic pH. And why am I having you do this particular one? Because it's the one that we make buffers with and everything, so you're going to be playing with it a lot in the next one. So NH3 plus water makes ammonium hydroxide, and we have 0.100, 0 and 0 minus x plus x plus x. Okay, now if you're tired of writing the ice tables now, this is probably a place where you can quit writing them because you can see what goes into the equilibrium expression. If you can't see it though, always write your ice tables out. All right, going to ignore. And it's less than 5%, greater than 10 to the minus 6. So we're okay there. Okay, now the difference here, this X happens to be the hydroxide concentration. And the POH is 2.89. And the pH should be 11.11. Okay. It's a weak base, so I expected a weak base pH. And let's jump over there. 11.11. All right. Does anybody have their lab from last time? Because I had you take the pH of 0.1 molar ammonia. Does anybody have that data that we could compare to?
I think we have some. Give us just a second. Do you want the ammonium nitrate?
No, so just the ammonia NH3.
Ammonia. I don't think we did it, and ours is in the lab, so we can't check it.
And that's okay, because we're going to take it again. But during the previous lab, we did this one and this one. If we wanted to compare what numbers we came up with. Does anybody have the vinegar, the 0.1 molar acetic acid written down from the indicators in the pH paper?
I remember doing it with the meter, and it was high.
And it was high. Okay.
Yeah.
So again, I won't put anything right here for experimental, but we'll test it again. But we will now expect these predicted numbers. Okay, so what is number 7? Number 7. Oh, is a dilution. So it's the ammonia with 0.02 molar instead of the 0.1. All right, so what is my purpose of making you do a dilution? I want you to see that the dilution should make it a weaker base, so the X should decrease. So the only difference is going to be my starting concentration right there. And I think I said 0.020. So it's 1.8 times 10 to the minus 5th x squared over 0.02 minus x. Going to ignore the x. And 6 times 10 to the minus 4. Going to check it. Mm, 3%. So that's okay. Okay, gonna plug it in. So this is 0.00. 0.00, how many sig figs? One more. Okay, so I'm gonna take the negative log. And remember, this is a POH.
Okay, I'm leaving this. Sorry, guys.
3.22, which makes the pH 10.78. Oh, wait a second. Did we expect it to get less basic? Yes, because it was diluted. If you dilute it, it becomes even weaker. So the identity didn't change, but the concentration did. So by diluting, I am now only 10.78. And then the next one is ammonium. So this was still ammonia. It was just diluted. Okay, this one will be ammonium, and this one will be a buffer. All right, over to the whiteboard again. Okay, the next one again, I don't care about the nitrate, that's just the counter ion. So this is a weak acid. And its Ka, I think is 5.6 to the negative 10th. Yep. All right, so 5.6 times 10 to the minus 10th is equal to x squared over 0.1 minus x. I'm going to ignore x. And 7.5 times 10 to the minus 6th. Let's check it. Oh, it's definitely valid. In fact, it's, let me see, 0.0074%. All right, go and plug it in. So 7.5 times 10 to the minus 6 and take the negative log. Is 5.12. Okay, did we expect an acidic pH? Well, yes, it's a weak acid. Okay, I'm gonna go plug this one in. So 5.12. Oh, I'm already there. 5.12. And then last but not least, we have this nice little buffered system. And it's 2 mils of each of them. So we're going to dilute to 0.050. And I'm going to do this one 2 ways for you. Okay, so here was the first buffer that we're doing. So I have 2 milliliters of 0.1 molar ammonia. And I have 2 milliliters of 0.1 molar ammonium. Okay, we still have to come up with an equation. And there's 2 things here, so just choose somebody weak. I don't care who you choose, and write its equation. All right, 2 mils and 2 mils, so M1V1 is equal to M2V2, so both of these are going to get diluted to 0.05 molar. We started with 0.05 molar ammonia. Did you add anything to it? Yes. Was it already part of the equation? Yes. It is a common ion. Is it the special common ion called a buffer? And in this case, the answer is yes. So I can plug it in to the equilibrium expression, or I could jump to the Henderson-Hasselbalch. I'm going to show you that it works both ways. Ignore the x's. Oh, look. 1.8 times 10 to the minus fifth. Okay. Now in this case, do I actually have to check it? You would check it to the one that you put on the left. So I would divide that by 0.05. To be completely correct, you would check it to both of them. And it's very valid. Okay. Okay, remember, this is just X. This is not the only part because the ammonia is 0.05 molar minus X, and the ammonium is 0.050 molar plus X. So I need to add 0.123418. And again, it is so negligible that it doesn't even matter. It did not change. And Le Chatelier told us that. Okay, Le Chatelier says that if we add a product, it should shift left. Well, if it shifts left, that means, so if it shifts left, that means less should ionize. And in fact, so little ionized that it didn't even change either one of the numbers. So what's the pH? Okay. Oh, well, this I found a hydroxide. So the pOH is equal to 4.74. So the pH is equal to 9.26. Okay, so that's using the long way. That's using the equilibrium expression. The moment I saw that this was buffered, I could have just jumped right to here. Oh, look, that's much easier. The reason for this problem is I wanted you to see about the buffer, but I also wanted you to, oh, I could have used the Henderson-Hasselbalch right here. Okay, both ways work. The Henderson-Hasselbalch is just a lot faster. Okay, so 9.26. All right, we just figured out the pH of every solution that we're supposed to see. So on Thursday, we're going to make these solutions, and I suggest we'll have one person do each of them. So not everybody will make all the solutions, but we'll have all of these solutions. One person will make each. We'll take the pHs, and then we can compare. Did it come up with what we expected or not? And the only reason, okay, the only reason it won't match is number one, because the meter is not working. And so we're going to test it on multiple meters. And two, the concentration in the bottle wasn't quite right. But that's why we're going to use multiple meters, is we want to see which ones agree with each other. All right. And then I had a wonderful little unknown for you. Okay. And then I'll still have an unknown for you. And then you can math backwards and just tell me what the proton concentration is. Okay. Now I know that doesn't seem like a very fun lab, but there's all your sections that I did on the whiteboard. Okay. Discuss how diluting changed the degree of ionization. Okay. How did it affect that X value? Well, every time you diluted, it got smaller because there was less to ionize. Let me see. Compare solutions 2, 4, and 6 and 9. How does the common ion effect influence equilibrium? Okay, Le Chatelier says that if you add a product, it needs to shift left. So let's go up here. Okay, 2, 4, and 6 and 9. 2, 4, 6, and 9. All right, so 2 and 4 and 6 and 9. All right. So in solution 2, it was 3.02. And when I added the protons, okay, when I added hydrochloric acid, it went to 1.3, and it went to 1.3. So the common ion shifted it to the left, but who's controlling the pH? The strong acid, okay, the strong acid. On solution 6, it started at 11.11, but when I added some of its conjugate acid, I dropped from 1111 to 9.26 because I shifted to the left. So the ammonia doesn't have as much effect, okay? Because I shifted to the left because I added a product to it. All right, that was pretty wordy. Any questions on what I was trying to get with that question?
I don't think so.
Okay. Let me see. Write out a balanced equation and compare the solutions 6 and 7. How does dilution affect the pH? All right, so all of those problems that we did with dilution, dilution makes the concentration go down, which makes it even a weaker acid. And then, of course, we can't do this one because we don't have our experimental values. So for any solution that didn't match. And then we can't do this one yet because we haven't done our unknown acid. Okay, that is the weak acid common ion and buffer one. We will also do the common ion and buffer experiment. No. Yes. Just like before. Come on. Lab is very, very short. Okay, so compare and contrast. What does common ion and buffer mean? Common ion means it's similar to both. Buffer is the special combination. And then 1 through 9, which will exhibit, where are my 1 through 9s? Ah, here we are. All right. So just like we did last time, we're going to take the pH of our 0.1 molar ammonia and our 0.1 molar ammonium. These are the same solutions that we had just done. Okay, so they shouldn't be different. Okay, but technically this is a new day, so you always want to check your equipment. And then we are going to make 50 mils, or we're going to take 50 mils of our ammonia, and we're going to take 50 mils of the ammonium, and we're going to make a buffer. Okay, so we're now going to have 100 milliliters of a buffer of 0.050 molar, because remember, it dilutes. We doubled the volume, so we halved the concentration. All right, so what is the purpose of this one? 10 milliliters of solution 3, which is a buffer, and we're adding 6 mils of water. The question right there is, does dilution affect the buffer? Now we know the answer is no, but I wanted you to actually see it in lab and actually do the number crunching and do the number crunching. So let me see, that's number 4. So 10 milliliters. You know, we're just gonna do it right here. So I took 10 milliliters of our buffer of 0.05 molar. And I added 6 mils of water. All right. Doesn't matter which equation you use. Okay, we're going to do it two ways. I'm going to do the concentration, but I know this is buffered, so I'm also going to go to moles. All right, so I had 10 mils of the 0.05 and I added 6 mils to it. So their new concentration is 10 mils times 0.05 is equal to 16 mils. What is my new concentration? My new concentration is 0.03, how many sig figs? 0.031. Oh, of this one and this one. Because when you dilute one, you automatically dilute another one. So 0.031 and 0.031. Guess what? The pH is 9.26 plus the log of 0.031 molar divided by 0.031 molar. The pH did not change because I diluted it. which was the take-home message. So does diluting a buffer change the pH? And the answer is a big old no. But the reason I had you do it is I wanted you to physically see that in lab. Go ahead and pour water in there. It is not going to change the pH of a buffer. But if you pour water in a weak acid or in a weak base, it will change the pH. Okay, but it will not change the pH of a buffer. All right, let's see. So that was number 4. Ooh, okay. Number 5, not only did I dilute it, but I also added HCl. All right, so 10 mils and 1 mil. So I had 10 milliliters of the 0.050 molar buffer. And then I added 6 mils and 1 mil of 0.1 molar HCl. So again, I don't care about the water because it's not going to change the pH of that buffer. All right, NH3. Okay, I know I'm buffered, so I'm getting tired of doing all those dilutions. So let's just jump straight to moles. Let's just jump straight to moles. So I have 10 mils of 0.05. Get out of milliliters. So one, two, three. So when I draw, okay, here's my total. When I pull out 10 milliliters, I didn't pull out all the moles I started with. I pulled out 0.12350 moles of the ammonia, and I also pulled out that many moles of my ammonium. Okay, the rest are still in this. Let me see. So how much is left in there? Okay, so there's still 90 milliliters of my buffer left. So I didn't pull out the total moles. I only pulled out as many are as in 10 milliliters, which happens to be 0.3 zeros and a 5. So what did I start with? 1, 2, 3, 5. Oh, okay. Good grief, I haven't even done any of the problem yet. I just needed to know how many moles were floating around in my 10 milliliters. All right, now what did I do to this 10 milliliters? I added HCl. All right, did you add something? Yes. Is it already part of the equation? No. Well, then you need to determine which piece is going to sop it up. Okay, this is a titration, but it just happens to start with an existing buffer. All right, so I have my protons, and it's going to react with my ammonia to make some ammonium ions. Well, how much ammonia did you start with? How much ammonium? And how much acid did I add? So 1 milliliter is 1, 2, 3 zeros. The difference is this is a titration because an acid and a base are being combined on the reactant side. Do I have enough base to sop up all that acid? Yes, I do. All right. Are you still buffered? And the answer is yes. So I can use the Henderson-Hasselbalch. Whoops, it was 9.26. Plus the log of the base piece. Now remember, I don't care where it's written. It's always the base piece on top divided by the. So I should expect this pH to be 9.38. Whoa, didn't change much, which is the point. Okay, a buffer is not supposed to change much. All right, here's the difference. When you only took a portion of the buffer, we only took a portion of the moles. So every other problem that I've ever done, I started with all of the moles that I started with. Okay, that was really a roundabout way of saying that, but I use all of the moles. Here, I'm not using all of them. I'm using only what came out in my 10 milliliters, in the 10 milliliters. And it's working pretty good. 9.38. All right, so which one was that? That was 9.38. All right, what's happening here? So I have my 10 mils of buffer. Who cares about the water? Okay, so that, whoops, that's just diluting it. And in this case, oh, sorry, I lied. That one goes up here. 9.38 goes up here. We can do the same thing with a different quantity of acid. This one is a base. So which piece is going to react with it? It's going to be the ammonium. And this one is a true, okay, that one is a true titration because it is vinegar and sodium hydroxide. And this one is ammonium and sodium hydroxide. Those did not start as buffers. So this one was just a weak acid. This one was just a weak acid. I don't know why I called ammonia a weak acid. This one was a weak base. This one was a weak acid. This one we made a buffer. This one we diluted a buffer. This one we did acid plus a buffer. So a titration technically with an existing buffer. This one, we did it again, just with more. Number 7, it was a base plus the buffer. And number 8, this is a mini weak acid strong base titration. And number 9 is another weak acid strong base titration. Again, the lab doesn't take very long. It's, do you know what you should expect? And do you get what you were expecting? And then here's the practical. Okay, there's the practical. So you're going to create your own buffer. It can be a pH of 9, pH of 5. So anything in the lab that we have used in these 3 different labs, you're going to combine together to make your own buffer. And then you're going to add some strong acid to it and some strong base to it and see what it works. So this one will be in your lab notebook. Okay. That one's going to be in your lab notebook. That's your practical application. Probably won't get to that on Thursday, so that'll follow into the next Tuesday. Oh, let me see. The solution was 2.87. It was 1111. What was number 3? Number 3 was 9.26. I got number 2 wrong. So this one was just the ammonia. This one was the ammonium, which I'll have to look back for that one. This one was the buffer. And then this one, we're adding things to the buffer. This one was just diluted. So we figured it was still 9.26. This one added acid to it. And what did we get? 9.36. And we didn't calculate number 6, 7, 8, and 9. Okay. All right. This one, I just need to look back into the previous one because it's just the ammonium. Does anybody still have that in front of them? The pH of the ammonium?
No.
Okay, I'm going to jump back and see if I can find it.
You wanted the ammonia.
The ammonium nitrate from the previous one.
5.110. I mean, 2.
Excellent. Okay. So those 2, we did them in the previous. We did them again. Hopefully it didn't change. But then the others, the buffers, we did make. These 2 should not change. Okay, those 2 should not change because that's just a dilution. And then this one is our acid. And then I'm actually going to let you do those just to make sure you can do it without me. Okay. All right. Questions or thoughts on what we're
I
going to
think
do
there's
Thursday?
No, I think there's a class coming in.
Oh, okay. All
I
right.
think. I don't know.
I will
Someone opened
just,
the door, but
yeah, go ahead. I will just see you all on Thursday.
all right.
Okay. Thank you.
Thank you, Jolly.
Bye.